Hello and welcome to College Physics 1, Lecture 20, Circular Motion. In our previous few lectures, we've gone through our individual forces once again and reintroduced them with equations. So we've seen weight and apparent weight, we've looked at normal force, we've introduced friction and drag and so on. But all of those problems that we've been working on have been linear, meaning just an object moving left to right or up and down. Here, we're going to introduce a particular type of motion, considering circular motion. That is, objects moving in circular paths. To begin, let's just kind of make a general statement about what type of motion we're really looking at. We're going to be assuming we are under uniform circular motion throughout our problems. And what that means is an object is moving in a circular path, but by saying uniform, we're stating that it's doing so at a constant speed. So uniform circular motion is the motion of an object at a constant speed in a circular path. But be careful, speed and velocity are not the same thing, remember. Velocity is a speed, but with a direction. And so that's important, because in circular motion, you could be moving at the same speed, but our direction is always changing as we move around the circle. So if our direction is always changing, so must be our velocity, because velocity includes direction in its description. So in this motion, we have a constant speed, but an always changing velocity. And that velocity always points tangent to the circle, meaning straight off of the circle. So let's first look at the image here on the right-hand side, just focusing on the green arrows. The blue circle you see is the path we take, and notice that we are moving, indicated by the blue arrows, in a counterclockwise direction. So at any of these black points you see here, our velocity is pointing straight off of the circle, tangent to the circle. Recall that the word tangent in this context means only touching the curve at this point. So right here in the bottom right dot, we see that our velocity is straight up and to the right. But then we're coming around to the top of the circle, and at this point we're moving leftward before we start to curve down more, and so on and so forth. So that is showing us that our velocity is always changing because the direction is changing. Well, keep in mind that if you are changing your velocity, then by definition, you are accelerating. Acceleration is a change in velocity. So if we're always changing our direction, in other words, we're always changing our velocity, we must also always be accelerating. Now, this is a point of confusion a lot of times for students because you keep hearing constant speed, but we're accelerating. So in terms of what we've discussed so far, we've only focused on situations where acceleration meant a change in your speed. But it can also mean a change in your direction. So just be careful with that. Now, the acceleration that we do experience is known as the centripetal acceleration. Centripetal is a word that literally translates to center seeking. So that hints at the fact that this acceleration will always point straight toward the center of the circular path. And this acceleration is given by v squared over r, where v is the speed of the object and r is the radius of your circular path. Right? So centripetal means center seeking, indicating at the fact that acceleration always points toward the center, as you can see by the orange arrows on the right-hand image. Okay, well, our discussion of circular motion means we get to introduce a few new terms. You've likely heard these terms before, regardless of whether or not you've had physics before, because they're fairly common terms. We're going to introduce period and frequency. These are both terms that correspond to motion that is repetitive. That could be a wave, waving up and down with crests and troughs. It could be something moving in a circular path like we have here, repeating itself over and over again. It could be a pendulum swinging back and forth, back and forth. All of these are repetitive or periodic motions. So we want to make sure we can define both of these terms before we move forward. Period is the time it takes for you to go around a circle one time. In other words, the time it takes to complete one revolution. Because this is a time interval, period is measured in seconds, just like any time we've used before. And the symbol for period is, unfortunately, capital T. I say unfortunately because if you recall from our past lectures, capital T also represents tension. So, as if physics isn't confusing enough, we're using the same symbol T for both tension and period. And sometimes they will both show up in a problem. So that can be a little troublesome. We'll see that in an example we do soon. Anyways, so period is the time it takes to complete one revolution. The number of revolutions every second, in other words, how frequent that thing is happening, is known as the frequency, which is given by lowercase f. Now, this is a confusing point as well. Frequency is the revolutions per second. But revolutions is not a unit. That's just a thing that you're doing. You're revolving. So revolutions isn't included in our units. If we were to state the unit of frequency, we would just say it is 1/seconds, or inverse seconds. Hence the per second. Now this is also commonly referred to as the unit of a hertz, Hz. But I choose to not use Hz in our lectures simply because I think adding in the extra letters of Hz makes it more confusing. I think things are more clear if we just leave it as seconds to the -1 power for our purposes at least. But for those of you familiar with any kind of frequency, this is the same thing as a hertz, Hz. Now, these two terms, period and frequency, are inversely related to one another, which if you recall from our math review, means one quantity is equal to 1 divided by the other. In this case, we say frequency is 1 over the period. And this should sort of make sense. I mean, think about the units here. We're saying frequency is measured in per second. Well, and now you can see why. This is 1 divided by the units of seconds. In other words, that gives you units of seconds to the -1. Right, so that basically proves the unit for frequency. Now, we can use these terms to help us find the speed of the object in a circular path. If you keep in mind that the definition from way back in the day, the definition of speed is distance over time. Well, if that's the case, the distance that you travel around a circle, in other words, the outer perimeter of that circle, is known as the circumference. So we're traveling the circumference of the circle, which is given by 2 pi r, where r is the radius. And the time it takes to go around the circle, we've just defined to be the period t. So if we wanted to say speed is distance over time, we could write that as 2 pi r over t. Or, because period is the inverse of frequency, we could also write this in terms of frequency as 2 pi rf. Both of these equations are perfectly valid. If you're given a period, use the first part of the equation. If you're given a frequency, use the second. So let's go ahead and use these terms to work out an example problem. Now, I really like this example, mostly just because it is relevant to a real-world application. The problem says that a hard drive disk rotates at 7,200 RPMs. This is a real speed of hard drives. Most HDDs or hard drive disks rotate at about this speed. Granted, today in the year 2021, a lot of us are shifting to solid-state drives, which doesn't have a rotating disk, but still, most normal computers have at least one of these hard drives in them. So we're also told that the disk has a diameter of 13 centimeters, and that it asks what is the speed of a point that is 6 centimeters from the center, and then what is its acceleration. Okay, well, the way I always tackle a problem like this is we need to understand what it's actually telling us when it says RPMs. So our goal, we need to think about what this actually is. 7,200 RPMs. Well, revolutions are per is P, M is minutes. This is 7,200 revolutions per minute. That should be an indication to you what this actually is. Per minute is indicating per time. In other words, this is how frequently the object is revolving. This is a frequency. 7,200, in other words, revs per minute. That's RPM. So that is very important to understand that when you're given something in RPMs, it's telling you per a certain amount of time, so that is a frequency, how often or how frequent it's happening. Now, because of this, we are given something in minutes, so we'll want to do a unit conversion to convert this to revolutions per second. So to do that, it's been a while since we've actually done a unit conversion. It's a basic one at least. We want to cancel out the units of minutes, so I'm going to put minutes up on top. And for every 1 minute, there are 60 seconds. By writing it like this with minutes on top, notice that the units of minutes cancel out, leaving behind units of revolutions per second. 7,200 divided by 60 is 120. Revolutions per second, but remember revolutions is in a unit, so we just call this inverse seconds. Okay. Now, it asks for the speed of a point 6 centimeters from the center. Well, we're given a frequency, and we're looking for speed. We just came up with an equation that relates frequency and speed. We said that the speed, v, is equal to 2 pi r times f. Well, we know what 2 and pi is. We know the frequency because we just got it, so we just have to make sure we know what the radius r is. Now, be very careful. This problem purposely tries to trick you by giving you two distance values. You're given the diameter of the entire disk, and you're given the distance to the point it asks about. Which means one of these is irrelevant. And in this case, the 13 centimeters is useless to us. It's asking specifically about a point 6 centimeters away from the center. So we need to make sure we apply that distance. So we have 2 pi times the radius, which was 6 centimeters or 0.06 meters, times the frequency, 120 inverse seconds. Now look at the units here. We have a unit of meters times seconds to the minus 1. That's going to give us the correct unit of velocity of meters per second. This comes out to be about 45 meters per second. Now you might be thinking, that's fast, because this is 100 miles per hour. But think about what we're talking about, a disk in your computer that's spinning 7,200 times every single minute. So we're obviously going to be moving very, very fast if you were, stuck against this side of the disk and spinning around with it. Even more impressive than the velocity, though, is the acceleration. From earlier on in the lecture, we saw that acceleration A is given by v squared over r. Well, this means we're squaring 45 meters per second. And not only that, but we're dividing by a really small number, which will make it even bigger. So much to people's, typically much to people's surprise, this gives you a very large acceleration of 34,000 meters per second squared. Now, I would say if this was given to you as your first homework problem dealing with something like this number would probably freak you out. you'd probably think you did something wrong because we've never seen an acceleration nearly this high before. I mean, the acceleration due to gravity is only 9.8 meters per second squared. The reason you're getting such a high acceleration has its applications because this is basically the idea behind a centrifuge. So if you've ever been in a laboratory setting, like a chemistry or biology lab, you've probably seen a centrifuge before. It's this little station on a table that will spin around at incredibly high speeds, typically to separate solid matter from a liquid solution. Well, perhaps now you can understand why they're spun around instead of just like launched back and forth really quickly. Circular motion can produce incredible accelerations. Okay. So I think at this point, I don't want to go into some of the bigger problems, so I think this is a good point to start doing some questions to close out this lecture. Excuse me, I'm sorry. I forget, we have one more slide before we do that. I wanted to include this one slide to kind of bring it all back to forces and Newton's laws. And so, if you think about it, the object is always accelerating, right? We have that acceleration always pointing toward the center of the circle. Well, if that's the case, by definition, Newton's second law, F equals ma, there must also be a net force that points toward the center. So, F and A always point in the same direction, so again, always toward the center of the circle. And so, from the old definition, F equals ma, well, the acceleration we have for circular motion is v squared over r. And so that is how we get this equation for force in circular motion. mv squared over r. So just like the term we used for the acceleration, this is called centripetal force, which always points toward the center of the circular path. So just be careful. One thing to note here, centripetal force is real. Centrifugal, which some people say is not a real thing, and centrifugal is a real term, but it's not a real force. Only centripetal force is a real force, and we'll talk more about what that actually means later. So just to be clear, it's this force that is holding the object into circular motion. This could be, say, a rope being spun around with an object attached to the end. It's the tension in that rope that's holding the object in a circular path. Which is why, if, say, the rope suddenly broke, well, your object wouldn't keep continuing in a circular path anymore. It would launch off in a straight direction away from your circle. So this is important to understand, the difference between, this circular motion and linear motion we've been discussing so far. All right, so again, to recap, your velocity is always tangent to the circle, but your acceleration and force always point toward the center of the circle. And the expression for the force is mv squared over r. We're going to apply this to solving some problems in our next lecture. So lecture 21 will actually solve these kinds of problems. But for now, let's actually do those questions I mentioned. Question number 1. A ball at the end of a string is being spun around in a horizontal circle. What force is producing the centripetal acceleration of the ball? Okay, so it's basically asking what force is pointing in toward the center, right? Because that's the one that produces the centripetal acceleration, the center-seeking acceleration. Well, the object that is pointing inward is the rope, or the string in this case, and so as a result, the force that's keeping it in place is the tension in that string. The answer here is D. It's the tension in the rope holding that ball into a circular path. Let's do another one. A ball at the end of a string is being swung upward in a horizontal circle. In this case, we want to know the direction of the net force. So, by definition, this is kind of just a trick. It makes you emphasize these ideas, the direction of net force is always, by rule or by definition, toward the center of the circle. That is always true. Okay, so again, F equals ma, where A is always pointing toward the center, so is the net force. Okay, next one. Out of 4. A coin is rotating on a turntable. It moves without sliding. At the instant shown in the figure, which arrow gives the direction of the coin's velocity? All right. Well, remember that we talked about the velocity always being tangent to the circular path. So if you're all the way out here, let me use a different color. If you're all the way over here on the right-hand side, and it's saying that we're moving in a counterclockwise direction, well, if that's the case, there's only one force holding this object in, but if that's suddenly gone, for example, we can figure out which direction the object would move. And at this instant, our velocity is straight upward. So A is actually the correct answer. That is the direction at this point. If it was over here, then our direction would be downward. Or down here, it'd be to the right, and so on. It's just repeating over and over and over in a circular path. But at this point that it specified, we are angled upward. So we see A being the correct response. And last but not least, a coin is rotating on a turntable again that moves without sliding. At the instant shown, suppose the friction force suddenly disappeared. Which direction would the coin move? Okay. Well, we just said in our previous example that the velocity is upward. So if that's the case, our object would have to move upward. So if the friction force disappeared, this would just no longer have a grip in toward the center of the circle. All it would have is this force launching it straight off into the distance. So in this case, the answer is A. Okay. I think that's a good point to leave it. We will split this lecture up so that our next lecture looks at solving dynamics problems with circular motion. So that's going to be a good lecture. I hope to see you there. Otherwise, thanks for watching and have a great day.